videos along the way, and then we'll jump into the content.
Hi, Denver Startup Week. I'm Ben Data, CEO of Food Maven and co-chair of Denver Startup Week, the largest free entrepreneurial event in the world, and it's only possible thanks to the support of our sponsors. We have nearly 40 sponsor companies who contribute to make DSW possible. Let's show our love for these companies today and all week long. Thanks to our title sponsors, Downtown Denver Partnership, JP Morgan Chase, Prologis, and Xero. Our track sponsors who have made all the great content you're hearing today possible: Battery 621 in the Public Works, Capital One Cafe, Colorado Lending Source, Friday Health, Quizlet, Exactly, Zayo, and Zestful. Our headline event sponsors are bringing you inspiration from around the country. Thank you to Wix, Kenzen, MAPR Agency, Obsidian HR, Kickstart Fund, Promontory Mortgage, Molson Coors, and Comcast. Finally, thank you to our partner and member sponsors listed on the screen. Thank you for your support of Denver Startup Week. Now let's get to it.
Quizlet is a global learning platform that provides engaging study tools to help people practice and master whatever they're learning. Every month, over 50 million people use Quizlet to study any subject imaginable, for school, work, or as part of their personal interests.
Quizlet is super efficient, and I often, walk to class with it on my phone or even just before I go to sleep.
Combining cognitive science and machine learning, Quizlet guides students through adaptive study activities to confidently reach their learning goals. Quizlet has over 200 employees across 3 offices in San Francisco, Denver, and London.
Being at the Denver Quizlet office for the last year has been pretty incredible. Seeing the office grow while maintaining its, core connections to our values. It's been an incredible experience to be a part of, seeing how humble, candid, and open everyone has been, and being part of a mission-driven company in a time of uncertainty has been incredibly rewarding. So I look forward to, what the future brings, because the last year has been a wonderful experience. Thank you, Quizlet.
Hey everyone, my name's Adam Bauman and I'm part of the Quizlet team here in Denver. I'm proud to work for a company that's goal is to help every single person on this earth become a better lifelong learner. One of my favorite things about working at Quizlet is how much we follow our company values. There's always learning opportunities. We encourage everybody to teach themselves something new, as well as help each other learn. Whether it's from art classes or lunch and learn talks on latest technologies, there's always something new to find and help yourself grow. And I really feel like that's one of the best things that any company can offer is growth and opportunity.
Hello, everyone. Welcome to Denver Startup Week. I'm Connor Swanson, the Developer Track Chair and member of the Denver Startup Week Organizing Chair Committee. Thank you for joining us for our first ever virtual Denver Startup Week. If 2020 has taught us anything, it's that we are more powerful when we come together as a community to share ideas that help make each other better. And here we are virtually showing the world what Denver is made of. At Denver Startup Week, we strive to make all of our sessions a space where attendees can connect, learn, and grow, regardless of gender identity, gender expression, race, ability, sexual orientation, and the combination of those identities. There's something for everyone at DSW. Thank you for joining us. With that, I want to reiterate my thanks to all of our Denver Startup Week sponsors, and specifically Quizlet, our developer track sponsor, for helping make this week possible. Thank you. I'd now like to introduce you to Scott Penberthy, a Director of Applied AI at Google for the Office of the CTO. Scott and I go back a long way, as he actually has some ties to Denver as a member of the management team at PhotoBucket all the way back in 2007. Things have come quite a bit, a long ways in Denver since those times. And I'm excited to reconnect with him and have him share some great content with us today. Thanks so much.
Hey, Connor. Can you hear me now?
I can hear you, yes.
Oh, good. My video seems frozen on your little thing there, so I'll make sure it's good. Is it coming up yet?
There you are. We see you.
Okay, good. Yeah. So anyway, thanks, Connor, for having me. It's great to see you again. I think I remember back in the FOC days, and I think Denver's just getting started, and now all kinds of amazing companies come out of Denver. I think today, what I done, we recorded it last night to make sure you have a nice consistent video, and I just want to give like a minute intro to this. We hear a lot about AI. And you see a lot from a lot of companies, everything from what you see in movies to, is it really for me today? And what I wanted to share is a story that's, I don't know, it's very much true to the heart now. I'm in California, and I woke up this week and I thought I was on Mars. I mean, you look outside, it was orange sky, it was cold, it was raining ash, and you're like, oh my God, right? And you look at this, and the reason I brought that up is that, passion amount as a kid has always wanted to go to Mars. I didn't realize it would happen this week. But as I look at that, I spent the last 3 years applying AI in fanciful ways of actually helping NASA with their moon mission and Mars mission. And I'm going to share some stories in this video of how we did that. And what I found is we went through these processes. AI is really helping me redefine science. They're now using it like an idiot savant, where it goes, hey, try this. And you try it, but you verify it scientifically before you actually execute. And so it turns out that's actually rapidly accelerating science. The same thing's now happening in business. And the same techniques that we deployed, I'll share a story of a young woman who never even touched ML before. I've played with machine learning. She then went from not knowing it to being a world-class researcher in machine learning to now actually full-time at NASA. And the point is that the technologies that are in this, you'll see what it can do. But then it's down to the point where it's literally, you can start this afternoon, this evening, start to use the exact same tools in like 3 simple ways to help a business like massively transform. And we're finding, Connor, is that what was once the topic of 10,000 people in the world know what this is, which is very small, and science is now heading into business. And we at Google, we're seeing businesses reap tens, if not hundreds of millions of dollars of value from it. And so that's what the story's about. And hopefully you guys find it useful. And afterwards, you can ping me on Twitter. I'll hook you up if you want to see how to go play with this. But if you know how to do simple scripting, you know how to use spreadsheets, you know how to use this stuff. So that's sort of the intro, Connor. And it's a new way to program, and it's really fascinating. I thought I'd share with everybody.
Awesome. Thanks so much. I'll drop your Twitter handle in here so folks can reach out. And with that, we will get going with this presentation. Thanks so much, everyone.
So let's begin. I call this talk Mars to Main Street. A lot of things, I as a young kid at MIT, I wanted to be an astronaut in the worst way. I really did. And when I went there, I failed out of astronaut training. My astronaut training, when you had to go you had to fly jets. And my eyes weren't perfect. So, also I couldn't do the pull-ups, but I don't like to focus on that piece. But at the time, my eyes weren't so great. And so I sulking campus, and I ran into some friends who were at the MIT AI lab, and I saw it, and I never looked back. It's just fascinating. We can make computers sort of emulate it. And a lot of it is coming your way, analytics. And so it began as, for me and for a lot of people, 4 billion people ago, there's a lot fewer humans on the planet back then. It's a 5 billion or so looking up, and for a brief moment, among Vietnam War, social unrest, and a lot of challenges we all had. Economies were tough, gasoline crisis. For a moment, we all came together and we watched us do something extraordinary. We landed on the moon. And that kind of defining moment for a generation, I think we're starting to see some of that now. We talk about, through SpaceX now returning astronauts first time into around the Earth. We're talking about taking 30 machines at once in parallel to go land on the moon. Putting tons on the moon, not grams, and then going to the same thing to Mars. So it began for a lot of like 50 plus years ago. And then this mega plan is like, how do we go to Mars? And the status today is there's, a few of us want to go to Mars. I get one of them. No one can afford it. It's just, crazy. And so what I'd like to do is just simply make it more affordable. And hopefully that's going to intersect with people who can actually go to Mars and start with states and then move on from that. And that's kind of the idea. So we just need just a 5 million % improvement in performance to do that. One of the first things is got to make sure you make engines themselves reusable. But I'm going to show you some things in the analytics side that give you that kind of performance improvement, that allow us to simulate and ask questions hundreds of thousands of times faster. And I'll walk you through someone right out of grad school, and she did exactly that. And if some of you have babies, or you know someone that has babies, that's the first multiplanetarian. I love that idea. This is the first generation that's going to grow up where it's normal to think of us as a human race on multiple planets. And that's the kind of legacy that you're leaving with all the work you do and data analytics and data today. That's the next generation. And they're growing up, and that's their frontier. That's their Wild West. The wagons they'll take are rockets, but they're born today. And if you do the same time comparison today and then in the future, it was just 50 years ago. And 50 years from now, which I think you may get to see if we're all lucky, and your kids certainly will. Someone else is going to be here on this video. It's going to look very crude what we're doing today, and the holochatting, and the ideas that we'll be able to be entangled and have quantum computing, storage we can do in DNA, storing all the data from a large company in an eyedropper of DNA. That's just 50 years from now. And what we're going to see now, I think, are seeds of that, right? So how do you get there? What's the world look like? What does analytics look like in the future? And I love this guy, William Gibson, famous science fiction writer. And what he said is, it's already here. It's already here. So 50 years from now. So something we're doing today is going to be around 50 years from now and prevalent. It's just not evenly distributed yet. And I think what you're about to see is a hint at that. And it's like showing you a microprocessor in 69, showing you the internet in 89, right? And I'm going to start with a skeptic. This is Megan Ansdell. Graduated Hawaii with honors. She came as an astrophysicist to NASA, and we were trying to help her out. And I was talking the same thing I'm talking to you, and I don't know what time it is for you, she's like, Scott, this is BS. I was like, no, we can use tensors and graphs. And she's like, And so she was part of a program that we sponsor with NASA called the NASA Frontier Development Lab. It's a lab run by an independent space fan and AI fan named James Parr. And he believes that AI and analytics are the microprocessor for this generation, in the sense that that's what's going to actually get us to Mars. That's where you get that 5 million fold improvement. Like we have the microprocessor, can we get with analytics? And so what Megan's challenge is that she had this problem. She was fascinated with finding other places to live, like a lot of scientists. And she said, well, can I go find a planet? And they're called exoplanets. And the way you find a planet is you look in the sky, and remember, it's analysis, and what happens is the brightness takes a dip, like you see here, over time. And if it's a bigger planet, it takes a bigger dip. Kind of makes sense. Problem is you've got billions of these things in the universe, and how do you know which one to look at? And so NASA, astrophysicists, and planetary scientists and more, over the last 4 decades, created this elaborate system. It probably doesn't look much different from some sophisticated systems that you've built or have seen in your enterprise customers. And what it does is it's a series of good physics, good analytics, and it's a data pipeline. Sound familiar? So you have data pipeline that flows through multiple different stages of refining features, doing different models, all sort of the standard stuff that you would use today. And at the very end, through a cascading series of models, they basically have these potential planets being predicted. And this is using good old statistics, good old physics, been around for a while. And the challenge now, remember we talked about making this different, right? How you program differently. We challenged her and said, you can do this differently, Megan. What you can do is you take what we've built as humans through really solid science, great analytics, and that's the system, that's our black box. And what you want to do is you encode the input into this system as something called a tensor. I'll show you what that is later. And then you have the output come another tensor. And the tensor is basically the signal coming from the telescopes. And the output is another tensor is a vector saying, show me where the planets are. Well, how does this work? Well, it works by observing multiple examples, millions of examples of how it happened before from our science, and learns a piecewise, nonlinear, high-dimensional approximation to what you see before. So if you're familiar with like Taylor series or some basic time series, you've seen this before. And so the idea here is it's much more high-dimensional, but the idea is, can it find a transformation function from your input tensor to the output tensor? And a tensor is sort of an n-dimensional vector, is the idea. And sure enough, it works. And she was able to find, using older data, 3,000 planets it hadn't found before. She's pretty excited. And I said, wow, you did that 8 weeks. She says, no, 6. Because the first week was, I think we're just getting accustomed where the lunchroom is and where everybody is and orientation. The real work was only about 6 weeks of work. From a standing start, having never really played with machine learning or the tools we use in Silicon Valley, where it's sort of becoming sort of second nature for a lot of companies. So the next thing is she found this and she's excited. And they said, well, wait, how do we know we can live there? How do you know you can live there? So if she's landing, how do you analyze what probability do I have that I can actually live there? And so the idea is, this is a visualization of the Mars rover landing on Mars. We're going to land on a planet. How do we know what's going on? And the way they do that is they look at some chemicals of life. It's carbon dioxide, methane, and water. And you can plot it, and you can sort of look at compositions of atmospheres that we can tolerate. And it has to be within a certain habitable zone. Too close to the sun, you burn up. Too far away, you freeze. So you got to be in the habitable zone, and your atmosphere has to have the right composition. And what you need to do here is you have to shine a light through this atmosphere, kind of like the smoke you have here, my gosh, in Silicon Valley today. If you shine a light, you need a spectrograph. And then you can match the spectrograph saying that's inhabitable, that's not, that's closest to Earth. The problem is there's so many different variations of this. She had millions that she wanted to try. And she said, well, I'm in line to go get computing at the mainframe, not the mainframe, at this large cluster we've built internally at NASA. Amazing machine. But she only got a window so much compute. And I said, well, why aren't you using, Kubernetes? She goes, I would use that. I said, well, it's in Fortran, it's on a mainframe. I said, okay. So we took the Fortran code and it reads from files back and forth. And we turned the file input to a JSON query, file output to an asynchronous JSON response. And we package it up as a Docker container. And then we can parallelize it. And we extend it with GPUs. I forget which one. I think we're using NVIDIA V100s at the time. And we accelerated with GPUs. And then we got 1,000 of those GPUs and the machines. We ran all the simulations needed to do for 2 years before lunch. And that's the kind of thing, what's nice about it is you just use what you want and you throw the rest away. And now you get into this thing where you've got analytics with incredible power on demand that you want to use for a period. And that's the new tool set that we're all going to use. Remember, this is the thing we see now that's going to be in the future. And so she did such a great job. She actually was awarded a scholarship by a benefactor in New York to go study exoplanets. She became known as one of the best machine learning people in astrophysics. And now she works full-time at NASA. And you do something like that kind of extraordinary work from a standing start in 6 weeks. You make friends. And she told her friends about what's going on. And this is a picture here of the following summer. And they're all sort of here at NASA Ames. And they said, well, let's give that a shot too. Except now, not just astrophysics, there are planetary science, climate science, materials science, all kinds of areas are now saying, can I use analytics to reimagine science? So not just analytics in terms of good science experiments, and a control group and a test group and stuff you know how to do, and good statistics. I'm thinking, no, the science itself is now benefiting what was initially used just for analytics. A couple examples of this. Someone said, well, let's take what Megan did. And if we're going to the moon, we're going back to stay. It's called going back to the moon for good. You're going to be there for a while. And if we're going to go back for a while, you kind of need resources because you want to do what they call in situ. It's kind of expensive to ship stuff from Texas up to the moon. And so the idea is, can you use resources that are locally on the moon for the experiments or for the habitats? As a test case, for multiplanetarians, they're going to do this on Mars and maybe the other moons around Saturn in the next lifetime. And so if you're doing this, one thing you do have is you have pictures. So you have a visual picture here. This is a visual spectrum. Actually a color picture, but just not a lot of color up there. This is a color picture of an impact crater. And I said, why show an impact crater? So, well, Scott, if you're looking for resources, here's a rule of thumb. Look where big things hit. And then if big things hit, chances are there's a big thing close by, and those big things may be full of iron ore. Like, of course, makes perfect sense. So you look for the big craters, and here's one. Then you can use some different scopes and get an elevation. And so here, blue is lower and green and brown's higher. And you kind of run this color spectrum here. I guess I use blue so it looks like water, but the idea is that blue is lower and green's higher. So you have the picture, and you get elevation. And then we have these sensors that can actually give you a ferromagnetic signature, which means it's like a metal detector that you heard about. So a big metal detector is sophisticated, can actually detect this. We use it for looking at the sun. If you have these three, the idea is, can we also do thermal? Okay, sure. That's another one. So we got thermal. So I'm getting different data sets that we then collaborate and we put together, and we coordinate those, calibrate is the word I'm looking for, calibrate them so that they're all looking at the same part. And you've got the image, you've got the overlay, and you do this a lot in data, right? Where you're taking data, looking at line for the same customer, line for the same entity. So we have to prepare the data to look like that. And then we got to figure out, is it iron or not? Now, if we're on the moon, you just take a stick and you hit it, and then you figure that out. You can't do that here. So how do you know how do you detect anything? Well, a neat trick is you can do clustering. And then if you have a few samples, you can say, oh, look how these things cluster in different groups. There's a certain interesting cluster mathematically, looking at simple clustering algorithms in high-dimensional space. They seem to be interesting. And if you look at that, maybe that is an area to go look at. And we have a couple samples from the cluster, so maybe that's indicative of something finding there. And so sure enough, we found, I think this is NASA working with local engineers and working with Google and NVIDIA and Intel and IBM, a bunch of others. We are able to go and find really interesting clusters around these craters of things that could be interesting. They wanted to publish this, and NASA said, no, this we're going to keep to ourselves because this is actually now highly confidential data. But so that gives me a hint that maybe they did a pretty good job. Again, tensors in were the stacked images, tensors out, iron ore or not. Just like we said before, planet or not, tensors in, tensors out, are flowing through a graph. See a pattern? Let's go a little farther. This is a picture of the sun. Sun's pretty amazing, the closest star. And the sun has these beautiful things that emanate, called a coronal ejection. And it causes space weather. So we actually had weather forecasters, and they talk space weather forecasters at NASA. And they're trying to figure out how to do analytics on that data. I said, what do you mean? I said, well, we need to figure out when that ejection comes from the sun, it actually goes past the Earth. And it has good news and bad news. The good news is we get these beautiful auroras that you may have seen if you're in the Nordics. And that's the good news. It's just this beautiful stuff that we get to see. And what that actually is the coronal ejection is passing through our atmosphere. The bad news, GPS goes out. Communications go out. So what you really like to do is know when this is going to happen. So if you're a boat in a storm, you can plan ahead and you sort of plot your course before it happens. You can take action to maybe not go into the storm right now, or maybe take evasive action before this actually hits. You can save a lot of lives. You can also save a lot of value in economies and have a lot of good for the planet if you knew when these disruptions were going to happen for traffic, for navigation, for all kinds of things. And so what they did is, again, this tensor trick. They took the pictures of the borealis and they put in little pictures. And they took the other sensor data before and said, if I take the picture and I have other sensor data and I can stack this together in a tensor, I can flow it through a graph and have it find the function to say, is it going to disturb or not a few hours in advance? Sure enough, they were better able to predict disturbances in GPS by combining the ability to see with other traditional analytics. Now, the analytics you know how to do, and what we're adding here is a new signal that was heretofore like impossible to use. And they did it with, just a few pictures here of this is just a small sample that we're able to do in the 6 weeks. And they could take a few different pictures of one part of the Earth where they actually had the borealis and use that. And that was actually, it correlated to the actual answer. So like, this is pretty cool. And so what they really want to do is take the entire Earth and all of those and have a stronger signal to understand what's happening and have a better AI model, analytics model, what's going on. So I give you a couple examples of Mars and space. We think this is sort of fundamental to how we're going to get off this planet, and how we're going to back it up, and how your babies and the kids today are literally going to be multiplanetarians. And what's going on here started a decade ago, where a few engineers said, Moore's law is going to end. Moore's law is going to end. And we can't keep up with the data, so we need a new way to program computers. And we'd like the computers to be able to program themselves. So what I want to do is I want to think of a new way to compute where my stuff on the left, this is about 3 or 4 people in 2009. The stuff on the left is quantum bits, What you're actually seeing there is the hydrogen atom and the stable waveform states of hydrogen. And it gives 4 stable states. That's 2 bits of information in one atom, 1 electron wave. That's your ones and zeros now. So instead of storing ones and zeros, let's store 2 probabilities. So we now think in shades of gray like you do. And then, well, how do you compute with these things? Well, we could do von Neumann, but we know that Moore's law is going to end, so throw that out. And instead, let's look at the time, 8 billion examples of how we do it. So look at the human and try to extract architectures that we can learn from, but we can replicate in silicon or silicon germanium or some other substrate and do it at massive scale and apply tremendous energy to it. So the inspiration here came from rockets. So I started with NASA. And rockets, the famous rocket equation is about mass displacement. What it means is if you throw stuff behind you, you get momentum to go forward. You throw it fast enough, then you go forward really fast. And you need to burn your own oxygen because you go out of the Earth. That's why these rockets have oxygen in them, because there's no oxygen, once you leave the Earth. And that's the rocket equation that's going to get us to Mars. Now, the rocket equation doesn't look anything like a bird, but we studied birds. And actually, the Wright brothers didn't, which I found interesting. I thought they did. And what they looked at is that you're actually, the Bernoulli's equation, you're displacing mass when you flow over a wing. And so by generalizing mass displacement and harnessing that power and providing rocket power to this, you're going to go to the moon. You can go to the moon and beyond. That's what we're looking for here. Think about your ones and zeros, your numbers in your analytics as probabilities on the left, stored in quantum state. And then the computing architectures are new on the right. And the calculus that represented this, you're familiar with calculus. You do differentials, you do first derivatives and stuff. That's sort of second nature for analytics. But now we need to borrow something from Einstein. When he was doing the theory of relativity, he had to represent both time and space, but wanted one simple language for that. Not T as a subscript, but T, time and space is the same structure. And used tensor calculus. And what a tensor is that it's both space and time. And a tensor is a vector. So here, let me show this as a canonical example. You probably know this, but let's just go through it real quick. Let's say I have a picture on the lower left. And I cut out a square. It's I can't quite see what that is. I guess that's a laundry basket with a dog in it. And you ask a question, is this a cat or a dog? Well, what we do is we encode it as a tensor. Remember all the examples I showed you before of NASA? This is your new X, and I'll tell you what your Y is in a second. This is your new X and like a regression problem, right? So what you want to do is you take the picture and you create a red, green, and blue, sort of 3 different square matrices, like an Excel spreadsheet. And each number in a spreadsheet tells you how much red, green, or blue. But you make it between 0 and 1. So 0, no red, 1, full red. Okay? Normalize it between 0 and 1. And you stack it, and that gives you a 3D tensor, right? 3 sheets stacked. That's your input tensor. The label is another tensor. What that is it's literally, a strip of numbers, like a column in Excel. 1 to 1,000. What you want to have that output is like, put a 1 in the column, in the row, which you think the thing is. So now what we want to do is we want to take the input tensor, which is a stack of, it could be millions and millions of pixel values, and the output is just a strip of 1 to 1,000. And now here's the pseudo magic, the programming part. What I do is now imagine you're in the spreadsheet, which you know, and you write a formula that basically takes every single cell and it does some math to it. It can take a couple cells, it can add them together, it can multiply it. Maybe it does a little fancy thing like as a threshold number, but low-level simple operations. And you multiply it by a constant. You can add a little. So you have these things you multiply or add to a few numbers, and it produces another sheet, sometimes smaller, sometimes bigger. So you can imagine, and take the sheet, then you do more formulas, and that goes to the next sheet. And what's happening here in the picture is I take the first one, every single pixel goes through that math, simple math. Then the next one has another level of math, and I keep getting it more and more and more smaller. And so now the final math just goes, okay, take these values, put together, and that tells you a cat or dog. You got to be kidding me. This works. Yes, this works. And what's interesting is the learning part is like fitting a curve, which you know. And so instead of y equals mx plus b, imagine that in 500,000 D, not 3D or 2D, 500,000 D, a billion D, a billion and a half D just recently happened. Big equation. That's all it is. And the learning process is taking and trying to fit that very complex high-dimensional equation to the data sets. And that's all that happened that I just showed you. Finding ore on the moon by looking at multiple sensors, that's just a stack tensor, output tensor, or not. Finding exoplanets, you have the input tensor, which is all the astrophysics data, output tensor at planet or not by pixel. And we trained it by, the middle part was trained by what humans did. And it found the exoplanet equation. So this is tensors flowing through a graph. That's the middle part. And that's sort of the new way to compute. But it's a general approximation to anything in the observable universe and the things that we model in business. That's the cool part. And if you look at this, remember I said we throw out standard machines because of Moore's law is ending. And now we have a renaissance of computer design. They talk, I think it's sort of it's an amazing time as an investor. It's an amazing time to be in the hardware market because now you're thinking about, well, how do I compute with tensors now? So this thing here looks a lot like a mainframe. It's not, I kid him a bunch, but it's a water-cooled special chip that does approximate computing in flowing tensors through a graph at crazy fast speed, 1,000 times faster than the fastest SIMD CPU available today. That, my friends, that's the rocket. Okay. Remember you said we were looking for an architecture. We found one. Is it like a brain? No. But it's an architecture. And we take the architecture, we put it on the rocket, and we're starting to see magic that scales with, or the intelligence of this, the smartness, the ability to approximate, scales with computing. Now, one problem is you can't build, well, some people are trying, to build a die larger and larger. I mean, some people literally are building dies the size of an old LP. I had this crazy town, but they're trying it. But you can't, that's still limited by the size of the fab. So you have to connect these together. So at Google and probably other places, but certainly at Google, we had to build our own fiber and we make sure we can actually replace fiber, the glass. And we then have a Navy to drag this across the planet because we know if we're going to reason on this kind of scale, we can't put it into a single data center. So we have to do super fast networking 1,000 times faster than humans do. And I once asked the head of network engineering, why do you choose 1,000? Why 1,000 times faster? His response was, oh, it just sounded cool. So, I love that. Now, if you do this together, I have confidence that working with you and putting this in your hands, that we as a human race are going to crack something that we're going to call general intelligence in not too distant future. Now, will it be as intelligent or you or I? Will it have feelings? Well, I know. What it'll enable us to do is be like an idiot savant for us, in the sense that you're working on a problem. The idiot savant goes, hey, have you tried this? And you're like, what do you mean? And you try it, and you're like, oh my God, that works. That's how NASA's using this. They're using it in science to say, we think an exoplanet's there. So they take the data that the AI predicted using that function, comes from the graph, tensor in, tensor out, and they validate it through like they would any other research result. So the AI becomes part of the research team. And what this chart is showing is how much the human race, this comes from Ray Kurzweil, how much the human race has improved computing for $1,000 over the course of time. And it's a log plot, which means it's exponential. You see this a lot in the Valley. And so I think as exponential improvement, we're passing Moore's law, but it's actually tilting up now. So Moore's law is dead, but we're innovating faster than we ever did before. So if that's Mars and space, and now analytics are a new way to program computers, because computers are now going to do analytics at their core in these new chipsets and new all networked together new designs, typically highly distributed because they assume distributed computing. That's your platform. It's really a continuum, but it's what you do all day long. That's what's so amazing to me about this. And it turns out that the data that we're dealing with that you saw at NASA that we're dealing with everywhere else, turns out 90% of enterprise data is unstructured too. 90%. Like video. I bet your customers don't even use video, or you do. I mean, some do. But the analytics on video, forget it. It's just too computationally expensive. Or they don't know, I don't have tools. Now, we can actually get into that. And so if 90% of the data is unstructured, what does this do to business? And some economists are saying, if you do analytics with that kind of data, and you can do analytics to predict planets, or just make a prediction about what customers want. If you can do that, what we're doing as a human race together is we're driving the cost of prediction to zero. Zero. If you drive the cost of a prediction to zero, it's free, essentially, a marginal prediction. It's also superhuman because it's reasoning in a high-dimensional space that we can't articulate. We can feed it the data, we can't quite articulate it yet. So we treat it like an idiot savant. Great idea, let me verify it. And what we're finding is that businesses become analytics first that win in this economy, where you have a product or an idea. And the first question is what puts you at the table with the C-suite. Because they will need to ask you, well, what would I measure? What would I measure? How do I tool my product? How do I add something to my product? I can get some data off it. Tell me, get an insight in terms of how people are using it. So how do I, so for NASA, it's like the mission. How do I get stuff off the mission? What data do I bring back? And for the web page, what do I track for your behavior? And so you have a product, you release it in the wild, gives you users, and NASA calls it a mission, and that produces more data. And then that helps you improve your product, and you spin that up very quickly. And the AI cycle comes from Andrew Ng, who one of the first teachers of this at Stanford. And what we need to do as a community, and I challenge you to help us do this. You've now seen this, and this is what you do. This is easy for you. Is that the idea is we need to make it so that people outside us, the business users you talk to every day, that hire you, that work with you, I want to make it so that it's as easy to use what's in your head and your analytics, and the business, the economics of the value of what you do has got to be as simple as pizza. Pizza. That's what I mean. We all know how, I mean, you can learn how to make pizza. I don't know, and with the quarantine, I've been making pizza lately. It's delicious. It doesn't really help my waistline, but I love pizza. And the problem is, I make a whole pizza. I want a slice. I don't want the whole pizza. I want a slice, but I don't go out. I make it in house. So, but the slice, I'll pay $1 for a slice. That'd be great. Now I know how to make a pizza. I can, and if pizza were my core as a business, I want to make my pizza. Thank you very much. Fine. But most businesses, they're not in the business of pizza. So what I want to do is for analytics and buy it like a slice of pizza. So it must solve a business problem where the economics are 10 times better than me doing it myself. So my pizza, I called the $100 pizza. I was buying all these ridiculous things from Italy, and I was having fun. But if you do it in bulk, you can probably make a pizza for $10, right? It's hard to make it for $1. But you buy $1 and it satisfies your business need. I'm hungry. But the person selling for $1 is still making money. That's how ads works, for example, at Google. We take the price down and then let the market set the price. And so the same thing could happen here. So let me give you a couple examples where analytics, the stuff you do, you can put it inside a business problem and you can help sell it by a slice. And when you have economics like this, like for example, when this is going to hit transportation, and you can go across town in an electric car that's autonomous for $0.25, that changes entire cities. And they don't care how it's done, as long as it's safe, and the economics are so powerful that overwhelms the technology. And that's what I think when you think about analytics is ours and our jobs. How do we make it so the economics are so powerful, they pull you in and they want to use it all the time? And I'll give you 3 examples we'll leave with, and then we can have some Q&A. The first one is it's pedantic. In business, everyone ever call a business? Of course you do. Now, would it be great if they pick up all the time? Please call us back. Don't call me back. I want you to answer the phone. Now, if you answer the phone, that's a cost function for a lot of businesses. And they want to answer it and be cheerful and engaging and help you with your problem. So if you do this, when they answer the call, they want to make sure they're responding to you appropriately. And this is an example from a company in UK, online grocer. And what they wanted to do is figure out which call should I answer? Because I got 2 calls, and if I only can afford to answer one of the 2 at a time, so which one? And the idea is we can use analytics to analyze this waveform here. It's a speech waveform, and produce a table on the right. This is Nancy calling. Oh, she's not too happy. Negative sentiment. You should definitely handle this. What's that waveform say? Where's my milk? What's the action I should take? Send her the package location by text. You can do this for under $1, and a call center costs you $10. That is money, because now you're taking all the analytics, everything else, and you're putting it into a slice that a business can use. And you see a number of investments in this space where now analytics are being bundled into the call down to an individual transaction. First example. Another example. Business thrives on documents. We all have them, right? We always talk, paper, pencil pushers, or, we don't do that anymore, but, there's like so many documents in business and forms but that's how business runs. It's how we write down evidence of interactions. And a lot of it's being digitized, but still you have these documents, we all have receipts and whatnot. So what you want to do here, it's the same idea. A lot of times in tax, let's take tax preparation, for example. A lot of tax preparers are done offshore or in these like South Carolina and areas of these old dead malls full of people. One screen is on this side would be a PDF image. On the other side is like SAP. And sometimes you can do RPA between the 2. But the idea is, can I take the document and type numbers into a spreadsheet? Very common. Well, if you take, instead of recognizing exoplanets and recognizing cats and dogs and recognizing, aurora borealis and impact on floods, you can say, can you find where the invoice number is? Can you find the company name and a balance? Yes, of course you can. If you can find exoplanets, you can find that. And so you could train on millions of documents and produce these things where now I can do documents for pennies and then QA it saying, is it not been rejected? Is it appropriate? And as a result, it's another slice of pizza, because it may take you dollars to do it, but now you can do it quickly with these analytics. The next way we're seeing a lot of this applied today is the customer inquiry. You're on the street, you see a picture of something, you see a video. Think of TikTok, think of YouTube, think of, all these videos. That's how the next generation is growing up. They're going to do business by video. They want to show you this. I want to buy this. And they literally send you a live video. Well, that's just a tensor. And you could take a tensor and instead of identifying moon ore, you can identify, oh, it's the naked bee, and we have that for sale, and here's what it is. And this is transforming retail search. And then you can do analytics on top of that, and then to basically help guide exactly for a local area, create models that work in particular areas of the planet, because we know you recognize certain things in one part of the area than in the Northwest that you might not see in the Southeast, for example. And then the last thing I'll leave you with is this. Spreadsheets of these things. I think it's, there's some quote about, you'll never take a spreadsheet away from me. I need this if I do analytics for a living. We live in these things. But that was introduced in 1979, VisiCalc. So what's this next thing? So if you're working with tensors, what's the next thing we're going to play with? And I think a number of you may play with this. What we think is happening is spreadsheets and docs got together and they had a baby. And it's still early, and we're trying to figure it out. But now you have a doc that has data embedded with it, and the compute is sort of naturally hidden behind it. Now, it's still got a long ways to go, but the idea is that I can send you a document that has the data analytics inside it, that you can play with the data and do what-if scenarios on live data, just like looking at a doc. It's like going to a web page. You don't feel the heft of Google search when you're on Google. It feels lightweight. That's the same thing for this. So your analytics will be embedded in the document, and we think this is the next thing beyond spreadsheets, where the AI notebooks become the lingua franca for exchanging information inside an enterprise. And your community, our community of analytics is where a lot of this is starting. And there are actually over 1 million examples of this on GitHub today, free notebooks you can download and see all kinds of ways to do simple statistics all the way to deep learning. And I showed this to some of the folks who run, let's say the real consumer products, say, 1 million, I had that before breakfast. Well, the internet was one at one time there too. And I think this is, like we said, the future's already here. It's just not evenly distributed, and it's kind of early. And the next thing you'll see is where, where one, and it's happening in the industry, where now they're using these techniques to not only figure out how to go tensor to tensor, they're now using it to figure out the graph itself. The graph. So tensor through a graph. You can now use algorithms to find the graph structure that gives you the optimal, the least amount of error. And so they call these techniques AutoML, or automatic machine learning. And this technique now literally puts the power of all the stuff I showed you. You can now do this in a single line of code in a scripting language. There's a company called Hugging Face that's doing this. We're bringing APIs together. There's a lot of companies now making it so that it's literally a single function call in a spreadsheet. And we have one which we applied to tables, which are basically sheets. And it can basically, using AI to find the AI, it has now become the standard way that you start a contest with Kaggle, because it's so exhaustive and it's tireless. It finds the best model known so far. And now you take the model from a contest and you start with AutoML that it did. And now you add domain expertise and find better data, clean the data better to get the model even more performant. And this has now changed the nature of how data scientists do contests on Kaggle. And then I'll leave you with, I think, perhaps the most exciting part of analytics is the stuff you do all day long, the stuff with numbers, with probabilities. This is defining new experiences for users. We're entering into an era where websites and mobile apps seem so 1900s, 2000s. It's the point where you want to be able to talk to entities and have them converse back to you. I have a friend at NASA, he's been to post these things on social media where you can actually put your face on actors, and it's hilarious. But that's a neat technique where basically the human face itself is a probability distribution of pictures. And now we can now start thinking about interfaces where you interact with businesses through video, much like we have this talk here. But this talk that I gave this morning, or actually my evening here, this is the 1950s equivalent of television. They're pointing a camera at me and I'm speaking to you. We haven't yet figured out how to really use it as a medium, where now we can take the AI techniques and add, augment, and everything else. And I think the people who are putting all this, that we're working with here, are going to take my video and add some other things to it manually. We're getting to the point where now the techniques I just show you will be in the video. And it's going to be a standard way to conduct business. And it's a new sort of video commerce that's coming. And you'll basically be able to talk to enterprises, and talk to businesses, talk to documents. So I hope you enjoyed this time. I certainly had fun telling you the story of how we go from Mars to Main Street. And here I'm on Twitter. If you'd like to ask me any questions or follow up, please do follow me on Twitter. And I hope to see you online. And again, thank you so much for spending time. And if you made it all the way through, congratulations. I appreciate it. It's hard to sit still during this. And I hope you stay safe and your family does, and have a good, safe holiday season coming up. And I really look forward to working with you all, and love to see you online. I'll see you guys later. Thank you.
Thank you all. I'm sorry for some of those technical difficulties. We will take the question that we got in on the Q&A and get that over to Scott and send it out to everyone. Thanks everyone for joining, and hope to see you at the next sessions along the way. Have a good evening. Thanks.